My name is William Schultz. I'm a PhD student working with Lars Bildsen at UC Santa Barbara here in California. And most of this works in collaboration with Yanfei Zhang, who's a research scientist at the CCA and at the Flatiron Institute. Today I want to talk to you about photometric variability and some recent 3D massive star envelope models we've been running. So I want to start off by thanking Dominic Bowman and all of his colleagues for him for his introduction on Monday, and all of them for their work recently. You can see this beautiful spectroscopic HR diagram of all their TESS massive star observations. And we can look at any of these stars and we see beautiful TESS light curves, which you can then take temporal power spectra of and get really high resolution power spectra. Particularly, you can see the excess high amplitude red noise at low frequencies. This is the characteristics of stochastic low frequency variability. And really, there's two possible causes of this currently under discussion. There's internal gravity waves where the internal core convection launches these G modes that propagate to the surface and cause stochasticity there. The other explanation is these near surface convection zones, like at the iron opacity peak, for example, excite turbulence, and that turbulence also makes its way to the surface and manifests as stochasticity there. Our models are only envelope models, so I can't say anything about the internal gravity wave production, at the core at least, but I can talk about these near surface convection zones as a possibility. So what are these convection zones really briefly? Basically, massive stars are quite close to Eddington limit, even at Thomson opacities. So if you have any increase, like at the iron opacity bump, you can generate turbulent convective motion there. If your gamma is quite close to 1, you can get transonic convection. Regardless, you can get dense plumes that are then pushed above the iron opacity peak, where the opacity becomes quite sensitive to density. So if you have dense plumes being pushed up to, say, the helium opacity peak, you can get inflated envelopes and stellar winds and a whole bunch of interesting dynamics, which Yanfei talked about in his 2018 paper. So I won't go too much into that right now. And these convection zones are ubiquitous to most massive stars in most times in their lives. So I think it's really important to fully understand the physical dynamics of these processes. In the bottom left, I want to draw attention to one of Mateo's plots from his recent paper showing the convection zones in the surface, near the surface of a mesa model as a function of time or its age. You can see here that there's this iron opacity peak convection zone, there's a surface convection zone, and there seems to be a radiatively stable region between them. And hopefully I'll also answer the question for you today of is this truly a stable region, or is there convective dynamics happening in this region? So into the nitty gritty, what are we actually doing? We're using Yanfei's radiation module in Athena++. Our method goes like this. We take a mesa model. We take the temperature and density near the iron opacity peak region, because that's in the center of our simulation box. We then reintegrate a radiative hydrostatic 1D integration, matching the inner boundary with mesa. We then use that as the initial condition, so we don't have to initialize convection in these models, but we still then blast that initial condition with a high luminosity, or a luminosity from the mesa model, keeping the internal mass within that inner boundary fixed and doing an R² gravitational acceleration. There's no rotation in these models, there's no magnetic field, we're using gray opal opacities, and we're doing solar metallicity. But most of these things can be changed quite easily, and we do hope to explore that parameter space thoroughly in the near future. So recently, we've been doing two different classes of models, which I'll talk about briefly. The first ones we did were in 2018, was Yanfei ran these global models, which are half of a star in phi and a quarter of a star in theta. And they take roughly 100 million CPU hours to run, so they're quite computationally intensive. We only have 2 of those so far. But they give you really good understanding of global dynamics of these envelopes. And then more recently, we've been doing very narrow box simulations, or what we call top simulations, which only take roughly 1 million CPU hours, so they're a factor of 100 faster to run. And our hope is that we can probe different regions of the HR diagram with these smaller simulations and understand how this surface convection turbulence manifests in different regions of the HR diagram. So where are we currently covered in the HR diagram? The colored lines are just some mesa tracks to guide the eye. But chronologically, it started with the star top model, which was in 2015, which is the cyan cross. That was just a plain parallel model, so we're not going to go into too much detail on that. The blue triangle and the red diamond are Yanfei's global models. He was trying to look at LBV dynamics, which I'll point you again to his 2018 paper. So they're quite bright for their mass, but they do show a lot of turbulent convection, and we can use that to understand the physics that's happening at these locations. And then the one I'm going to talk mostly about today is this M35 Top Model, which is down here at around the 35 solar mass track. And it's about halfway up the main sequence, which overlaps really quite well with a lot of the TESS observations that Bowman and his collaborators have done. So briefly, before I get to photometry, I just want to say these simulations can shed a lot of light on the turbulent convection. I've already published a paper last year describing how this turbulence decreases the effective radiation pressure gradient. And that's essentially, if you take into account the correlations you see between radiative flux and density, that reduces the radiation pressure gradient because you have a change in the effective opacity essentially. But if you take that into account with the psi parameter, which I'll just point you to my paper to talk about or to read about, you get an order of magnitude correction in the relative error, which is quite substantial. And also recently, we've actually determined that there's two different types of convections happening in these surfaces, which was alluded to in the discussion yesterday. At the iron opacity peak, there's normal MLT-like convection where we have dense plumes falling down and warm, low-density things moving up. But above that and still below the surface, you have these dense regions that have become, where the opacity is becoming quite sensitive to density. These dense regions get accelerated quite quickly. So you actually have dense blobs moving up through a medium of low-density things that is kind of moving down or moving up less quickly. And we think all of these turbulent dynamics is really important, especially in our 1D stellar evolution models. So part of the work I want to do in the rest of my PhD and maybe in the future is to try and take all these 3D physics and try and map it into 1D stellar evolution models so we can get better stellar evolution predictions. But while we were analyzing these models from 2018, shown on the light curve, we were looking at the light curves that were shown on the left. And then when Bursons published his paper in 2020, we noticed that the timescale of variability in the bright O stars from their paper was quite similar to the timescale of variability that we saw in our already completed models. The amplitudes of variability might have been different, but again, our global models were in quite a different region, the spectroscopic HR diagram from their models with different masses and everything. So we decided that it was time to take our modeling method and just change the initial conditions so that we could then probe the region of the HR diagram where all these TESS observations were being taken and see if these convection zones can play a factor in and we can match. It would be amazing because we can match our light curves to actual observations. So I'm going to try and play a movie for you. It'll probably be glitchy, and I apologize in advance for that. But this is the best way to show the variability of these stars. So the color here is the probability at a fixed radius of that value. So if you integrated the color along a vertical line or a radial slice, the sum would be 1. The panels are density, temperature, opacity, and the magnitude of the velocity. And I'll start with the opacity here. So you can clearly see the iron opacity peak at around 12.5 solar radii. And you can see the helium opacity peak being excited and causing some turbulent motion and pressure waves being pushed to the surface. The gray dotted line is the Eddington opacity. So the opacity you need to have an Eddington ratio of 1. And you can see we're kind of crossing that in the 3D model. Moving up to temperature, you can see the temperature changes a little bit as a function of time. And you can see the black line, which is the photosphere, changes quite drastically as a function of time. And this will lead to some of the photometric variability, which I'll talk about in a few minutes. The density, you can see there's quite a contrast in density of several orders of magnitude at a single radial location. And you can again see these plumes that are being shot up in density that really dynamically change the density profile. And then lastly, coming back to the velocity, you can see the iron opacity peak convection zone creates velocities of around 10 to 100 kilometers per second. And those velocities persist all the way through the surface of the star. So I think we can definitively say that there is, in this mass of the star and above, the Eddington ratio is high enough that there is no stable convection, there's no stable region above the iron opacity peak convection zone. Even though radiation transport is the dominant energy transport mechanism in this region, there are still turbulent dynamics that affect the evolution of the models, and we really need to make sure we take that into account in our 1D stellar evolution models.
2 minutes, William.
Okay, perfect. Back to photometry though. If I put an observer at the edge of this box, I can say how much flux do they see or what's the luminosity they see. And so here's the small patch variability. It's quite a small number because this is 1/400th of the stellar surface that we're modeling. But even here we see 5 to 10% fluctuations. But again, this isn't really helpful to matched observations. So what we did is we took this patch, we tessellated it over half of a sphere, and we assumed that each patch was uncorrelated with its neighbor. So then we randomly sampled in the temporal domain. And then we combined it together to make this synthetic light curve that's more of a 3D projection. You can see that we have this high frequency variability that has maybe a few percent amplitude, but there's some stochastic variability on longer time scales that seems to be about 1% fluctuations. Quickly comparing to observations, here's again is this spectroscopic HR diagram. The cyan star is where our model lies. Zooming into this box, we can see that there's 4 O stars that are quite close to our observation. So if we scrunch our light curve together to get similar temporal domain, we can do a direct comparison to the TESS observations. Again, we see a kind of a high frequency variability that's not really apparent in the observations, but if you kind of look at the low frequency stochasticity, you can convince yourself that it's there, but we can do one better. We can take the power spectrum. So here, the blue is our power spectrum from our simulation. And the other colors are the SLF variability power spectra fits from Bowman's 2020 paper. We see comparable amplitudes at low frequencies, and we see similar slope of drop, even though we do have this excess because I haven't done any pre-whitening effects. But I do hope to do that in the future. But basically, I think the final takeaway is that we can qualitatively see SLF variability being produced by these surface convection regions, even when internal gravity waves aren't modeled at all. So I want to leave you with one more thing. I'm a little bit over time, but this is a project in its infancy. We've only done one model. We're doing more models. We hope to do tens of more models. So please just watch the space, and I'd love to take any questions you have. Thank you for listening.